Hello students, I hope you're having a wonderful day. Today I would like to complete a practice problem with you from Chapter 1. So remember, Chapter 1 is titled A Physics Toolkit, and it covers an algebra review, graphing review, and a dimensional analysis review. So I would like to complete a problem that requires us to calculate the position of an object given at a certain time, and we also have to graph some ordered pairs. So what you see right here on the left-hand side of the whiteboard is a T-chart. We have time and position, and remember, whenever we have a T-chart in algebra, we learned that we had X in the left-hand column and Y in the right-hand column. In the left-hand column, we have our X values. So for example, we have X1, and then in the right-hand column, Y1. And this makes up an ordered pair that we're going to plot on the graph. And then we'll just continue on. We have X2 and Y2 and so forth. So on the left side of the whiteboard here, we have a T-chart. In the left-hand column, we have our independent variable. So we have all of our X values. So I'll just go ahead and write X right up here. And in the right-hand column, we have our Y values. Okay, so we have time as our independent variable, and we know that we're going to plot our independent variable on the x-axis, and position, that is our dependent variable, that's going to be plotted on the y-axis, and these are ordered pairs. So let's go ahead and take a look at number one. It says title each axis and plot the ordered pairs on the graph. Well, we know that our independent variable is time, so let's go ahead and title the x-axis. So I have time, and I have units of seconds, and then we have position, that's our dependent variable. So I have position with units of meters, okay? And we're provided some ordered pairs here. So let's generate a scale. So our maximum value for our data is 2.4 seconds. So what we can do is just go up by, let's increase at 0.2 seconds. So I'm going to start out with 0. I've got 0.2, 0.4, 0.6, and so forth. Okay, and that is time in units of seconds. And then, looking at our y column here, our maximum value is going to be 27.5 meters. So I'll just put our maximum value on the y-axis at 30. That's going to be 30 meters. I've got 20 here. I've got 10 here. That's 5, 15, and then 25. Okay, we've got something like that. So in number one, it says plot the ordered pairs on the graph. Okay, so we have a position versus time graph. So at 0.4 seconds, we're at a position of 1 meter. So I'll place my ordered pair there. At 0.8 seconds, we're at a position of 3.1 meters. And then at 1.2 seconds, we're at 7 meters. Right there, okay. Our next ordered pair, at 1.6 seconds, we're at a position of 12.5 meters. At 2 seconds, we're at 19.2. And at 2.4 seconds, we're at 27.5 meters. Okay? All right, so we've done that. What we need to do now is create a line of best fit. Okay, so we'll start at our origin here. And we have something that looks like that, so it's definitely nonlinear here. Number 2, it says identify the relationship of the graph. Well, just quickly looking at this, we can tell that we have the shape of a parabola. And a parabola, the shape of a parabola, describes a quadratic relationship. So we have a quadratic relationship. Now, one thing that we need to be very careful of is when we identify the relationship, we don't want to describe the shape of the relationship. So the shape is a parabola. And if we called this a parabolic relationship, that would not be correct. The correct terminology is a quadratic relationship. And if we describe the shape is a parabola. Okay, so we have a quadratic relationship. Number 3. Identify the independent and dependent variable. So the independent variable is always graphed, it's always identified on the x-axis. So let's do our independent variable first. So independent variable, this is going to be time, and we have units of seconds. And our dependent variable, this is going to be position in units of meters, okay? So independent variable is time, our dependent variable is position. Remember that the independent variable is the variable that is changed or manipulated in an equation or an experiment, okay? So our dependent depends on our independent variable. All right, moving on. Number 4. Is the slope positive or negative? Well, whenever we describe slope, we know that the slope is the rise over the run. So this is delta y divided by delta x. So remember that we read the graph from the left to the right. And so our y2 variable, our y2, we know, so y2 minus y1 divided by x2 minus x1. Now, we cannot use this, okay, because that would be a straight line between our ordered pairs, okay? But delta y divided by delta x describes what's going on. And so let me go ahead and erase this here. So our y value is continually increasing, okay? So our values are increasing. That's going to give us a positive value in the numerator. So that means that our slope is positive. So we have a positive slope. Okay, number 5. Identify the units of the slope. So I mentioned earlier that we can't use y2 minus y1 divided by x2 minus x1 because we do not have a linear relationship. But we know that slope is rise over run, and rise is the change in y, so we need to take a look at the units for our change in y. That's meters. So we've got meters divided by our change in x. We have units of seconds, so meters per second, and these units cannot cancel out. So our units of the slope is meters per second. So slope identified by lowercase m, we have meters per second, okay? And number 6, how far does the object travel in 3 seconds if the function is d, so that stands for position. Position is equal to 4.651 meters per second squared times time squared plus 0.303 meters per second times time. So what let's do is let's plug in our value for time, and our value for time here, it's asking us about 3 seconds. So we have 4.651 meters per second squared times our time of 3 seconds. So I've got 3 seconds, and that quantity is squared, plus 0.303 meters per second times t, which is 3 seconds. So 3 seconds, our time value, is our independent variable. So 3 seconds, all right? Now, before we multiply 4.651 times 3, we have to obey the order of operations. So we're going to square this value. But not only are we going to square our numerical value, we're required to square our unit value. So 3 squared is 9, and seconds squared, so seconds times seconds is equal to seconds squared. So I have 4.651 meters per second squared times 9 seconds squared plus, now I'm going to multiply 0.303 times 3, and that's going to be 0.909. Now let's take a look at the units here. I have meters per second times seconds, and algebraically, this seconds is seconds over 1. So what I have is meters in my numerator, and then seconds in my denominator here, times seconds in my numerator, and then I have 1 in my denominator. So we have seconds in the numerator, that cancels out with seconds in the denominator. So I'm left with units of meters. Okay? So moving on. Now I've got 4.651 times 9. So let's get out our calculator here. 4.651 times 9. This gives me 41.859. Now let's take a look at the units here. I've got meters per second squared times second squared. And once again, algebraically, this is second squared over 1. So my units of second squared will cancel out here, leaving me with units of meters. So I've got 41.859 meters plus 0.909 meters. Okay? So we're going to add these two values, and we can add these two values because they have the same units. If they did not have the same units, we would not be allowed to add these two values together. Okay? So this gives us a position at 3 seconds. So I'm going to use a subscript here to describe my time. Position at 3 seconds is equal to 42.768. And we have units of meters because meters plus meters is equal to meters. Okay? All right, so after this object travels for 3 seconds, and we have a quadratic relationship here, at 3 seconds, the object is in a position of 42.768 meters. All right. Well, I hope this review with quadratic relationships has helped you today. As always, if you have any questions, you can always call me, you can email me, or you can send me a Canvas message, and I will get back with you as soon as possible. I hope you have a great day.